See how many things you learn out there. I was going to start with a joke, but then I thought my presentation will be enough for that. Okay. Hello. Thank you very much for turning up. You know, there is nothing worse than the pre-lunch session, than a post-lunch sessions. There you go. So, and my task is to wake you up, but let's keep it entertaining. Okay, let's start with my beautiful first image there. Since I have very little time, I'm taking advantage of the first slides, make the most of it. As you can see, I think I can do with this without breaking my neck. And of course I can't. Is it on? The laser doesn't matter. I can talk enough. Okay, so this is the moment. What I'm going to show you today, it's essentially a new image. Some of you might have seen this before because I presented this image, this new map of the lunar surface before. And we published a paper last year showing the microwave data coming from the Chang'e 2 Chinese mission, which has been going through some phases. It's about 10 years old now, but we had some issues with calibration. It's been calibrated, it's been published, it's been accepted by the community. As I said before, last year we published a paper on the lunar far side. What I'm going to do today is to show you the same data, well, revised and improved, of course, of the lunar near side, which is something we are all more familiar with. Some of you have contributed to some of these images here, which again, let's start from here. As you can see, the moon, the central one, the big moon is the topographic pulse color image, in a sense, of our moon. And the others are some of the maps which derived from multispectral data. And the multispectral data, most of these, except for a couple of exceptions, of course, are from UV visible and near infrared data, as you can see. And then from this data, what they do, we derive composition, actually quantitative, if I pronounce it properly, descriptions of the lunar surface. Again, it's in terms of iron, it's in terms of titanium, and so on and so forth. And some other derivatives, like the rock abundance one, the one down about 4 o'clock. Well, I don't even know how to read the clock, but the one with the rock abundance is derived from infrared data and the differences in temperature between day and night. And then you go up, finally, fast neutron is through gamma rays and so on and so forth. I'm going to show you some gamma rays images. And the top one is the new one. Okay, finally, our clockwise journey there. And that's what I'm going to show you with a little bit more detail. I can't give you background in this kind of talks, but just to give you, as I used to say when I was younger, a flavor of what we are doing now. So this is the mapping of the principal Mare on the lunar surface. This is Oceanus, Procellarum to the left, the one which is a known basin. And then the Imbrium, of course, which you're most familiar with. And on the top panel, number 8A, you can actually have a look of the orthodox mapping of lava flows, or the latest lava flows 1, 2, or 3, with the, Scarborough Shaba, I never know how to pronounce it, probably from 1973. Then Procellarum was mapped, the flows, Mare flows from Whitford-Stark and Head, and so on and so forth. And then the other versions are very familiar. Of course, there is Kissinger's, the C, and that's I put the latest one, which is the D map, the latest lava flows, which are from a colleague from China called Xian, and from 2023, which based his classifications to a work I collaborated with Zhang and the others, and others, yes. Okay, so anyway, just to show you how complex has been the classifications and how much interest this area of the moon has been given from the decades and decades, of course, because that was our friend Galilei discovered and mapped for the first time so many centuries ago. Just a blow-up version of that, very quick one to have a look. And as you can see, well, I don't know if you can read it, both Hissinger's and the latest data based on crater counting statistics, they classified some of these flows as the youngest on the moon. As I don't know if you can read it. Probably you can't, but I can read it here because I got a monitor. It goes from 1.2 billion years to about 2.7, of course, older than those. And they are in a geological a frame of the moon and planets is exceptionally young, believe it or not. 1.2 billion years ago is like yesterday for us. I wish it was the same for my age. Okay, we have now a little focus on what I've been doing. So the images on the top left, the A is the actual, this new map. What I'm going to show you in a second what it means. That basically it's a brightness temperature, which translates to humans as temperature of the lunar surface. Although you're using 4 channels, which different penetrative power. So we're using microwave, the 2.4 gigahertz kind of range, which is the Wi-Fi and microwave oven. And we use the 3 gigahertz, which is very close, and it can have a potential penetration of up to a few meters on the lunar surface. So it's very cool. You can see below the surface. That's the whole point, the excitement of using microwave, which is part of radar range. What I used here is a difference between night and day temperature at the frequency which has the maximum penetrative potential. I say penetrative again, I'm gonna drop my tongue. These are the images which are focused on the other data points. This one on the B, as you can see, is that titanium. Then you have the C. I'm trying to use the most diverse range of data that I could get hold of. And for instance, the iron map, I use the gamma rays version of it, which has a low spatial resolution, but a higher potential of penetration, as we will see in a minute. I say that again. And the D is coming from the infrared. This is part of a big paper, which I just finished. So I'm trying to condense the meaning as quickly as possible. So this is the actual map. I'm talking about the microwave temperature differences of the most of the lunar near side. What I did as good geological background in practice is I drew 2 lines that got all the composition, as much data as I could on AA and B lines. Plus I selected points here. It's got P215, which is the highest temperature differences points that I could find, and then some other sample points. Anyway, loads of data made possible also from QuickMap, which is a fantastic platform. And that's the readings from the cross sections A and B. And that's actually the data. I plotted the data for, as you can see, is iron, titanium, albedo, and obviously plotted against our microwave data and see how it varies across the 2 axes. And there are differences. And again, unfortunately, I can't spend hours and hours, but I'm going to say something about these at the conclusions. We have very limited time. So that's what it looks like. Please notice a curiosity that, for instance, when I plotted the albedo map coming from laser data against the iron oxide in terms of weighted percentage, is basically identical once you so the albedo and the quantitative estimation of the lunar surface is essentially identical. We would expect to know. And in the top one, I'm comparing titanium and iron from 2 different data sets. Again, follows the kind of trend. And the bottom ones is the key point of my research, which is to compare it, to interpret what the microwave is actually telling me, which is the most important thing. And I plotted against the titanium. There are similarities, which again will take an hour just to go through all of them. And peculiarly, well, it's not peculiarly, it's expectedly in a sense that ones that corroborates closer is the bottom one, which is I call it gamma ray FEO. So because again, that is a deeper potential than just the ones detected from ultraviolet, visible, and near infrared. Let's remember that what we're looking at, all these maps, are always the top skin deep surface, the powder regolith that really up at top, because it cannot penetrate deeper than that. So all these geological maps we have is essentially the dust that we are mapping. Controversial. These are the P points, which I highlighted before, and the other points. Obviously, we cannot read through them, but that's just to give you an idea how many parameters are used to compare them. There is everything I could find that of any kind of scientific value. Here we go. So I can do it. If I speak even faster and non-comprehensively than that and making more stupid jokes. Then is the comparison between what affinities, what correlations between the different data sets. And I'm going to discuss them at the end. This is the penultimate one. And then actually looked at this point, the affinity between the points in terms of correlation. And again, I'm going to discuss this in the very last slide. And then what I compared was if there were any differences between the Procellarum, which there were, and the Imbrium basals in terms of all these 20 parameters. And that's the conclusions. See, I did it. But I'm not going to read it word by word because most of you cannot read. That's what people do. No, I'm joking. So what are the conclusions? The first one is the highest temperature difference, remember, day and night, or using this channel, using the microwave data, which can penetrate up to some meters, represent relatively higher titanium, not unexpected, low calcium pyroxenes, rock abundance, and the slope angle. That was a surprise, which there is a correlation between slope angles and microwave outputs, which again, I could not. Again, this is work in progress, of course. Another strong correlation is rock abundance. These are not great discoveries. We know the two are together. There are strong regional differences between Procellarum and Imbrium, of course, mostly to do with plagioclase, calcium pyroxene, and free air gravity. Something already mentioned, I don't need to mention that, is by comparing albedo, iron, titanium images from completely data sets are basically identical. You know, within the correlation and anti-correlations, of course, that, you know, the albedo and iron is basically the same, just inverted, anti-correlation, whatever you want to call it. And that's my final conclusions. Again, I'm open to discussion, whatever you want to discuss that. If you want to discuss that, is how reliable then all these data we know on the moon on the lunar side, which are based on color differences in the visible and so on, that we draw all these maps. I did in my PhD 22 years ago, and then we create counted them, and then we dated them. How all of this is based on something particularly meaningful or less meaningful. Thank you very much.